Hello, everybody. So today we're going to be finishing up our conversation on pure phase transitions by talking about other ways we can look at phase transitions besides the ways we've talked about lately, which is mostly focused in on chemical potential and the location of the phase transition in pressure, temperature, space. So again, so far we've been mostly focusing in on the change in chemical potential, describing the physical properties, especially pressure and temperature, along these phase boundaries, helping us to identify and locate them, but also looking a little bit at the change in these physical properties, again, just for a pure species. So far, no mixtures. That's next time. But one of the important things that we also uh, need to look at is how these physical properties can change as I essentially go past a phase boundary. So as essentially I heat a system from one phase to another, what sort of changes in the physical properties and other thermodynamic properties can I expect? And the definitions of how these properties change across a phase boundary is essentially the uh, is essentially the building blocks of what's called the Ehrenfest classification system. So these essentially describe how phase uh, how the properties of a substance change as I go past a phase transition. So one of the important things to remember is so far when we've been looking at chemical potential, all of our phase transitions and all the ones in existence have a continuous change of chemical potential across temperature. So again, this makes sense because by definition, a phase transition is going to occur when the change of chemical potential is zero, and we expect all substances to have a continuous chemical potential to be a continuous function with temperature. However, one of the things you have to watch out for is that a lot of other properties don't have a continuous change across these phase transitions. And this is one of those things that actually has helped us describe a lot of these properties, including volumes of transition, usually a non-zero value, enthalpies, entropies of transition, which are also non-zero values, and heat capacities, which are honestly just a little bit messy. So again, let's go ahead and examine what these look like. So if I go ahead and I heat a system and I go from, say, solid to liquid, I'm essentially stabilizing the chemical potential of the system. I go to the liquid phase, and now I'm moving at a different slope. So we have two different slopes. So we have two different slopes, and essentially these where these slopes overlap is where the phase transition occurs. But by definition, this means that since I have two different slopes, I have two different entropies. So when I reach when I reach the phase transition, the entropy of the system spontaneously undergoes a big jump, and then it starts changing again. And because entropy and enthalpy of transition are going to be related, we see a very similar phenomenon with enthalpy. But one of the important things to remember is that this discontinuous behavior of enthalpy is often how we identify a phase transition to begin with, because I go ahead and I heat the system, and then I look for the point at which the temperature stops changing as I add in more heat. What we're actually doing is looking for this point where you have to add in a whole bunch of enthalpy, but I see no temperature change. This is the classic melt temp experiment. And it works because most phase transitions are first order Ehrenfest transitions, where they have these discontinuous properties with enthalpy and entropy. And the discontinuous function of volume is indeed one of the fundamental features that actually shows up in our Clapeyron and Clausius-Clapeyron expressions, because we do model the um, the change of pressure and temperature as a function of the uh, change in volume of transition, indicating that we do see this uh, discontinuous jump in the change in volume as I have to reorientate my system, and it often ends up, say, growing. So if I go from, say, a solid to a liquid, what we're often finding is a rearrangement of the lattice, which takes time and also involves a change in bonds, thus a change in enthalpy. However, what often gets a little bit messy is if we look at heat capacity. So when I'm looking at, since heat capacity is more or less the first derivative of enthalpy, which in and of itself is a first derivative of chemical potential, because I see essentially a since I see a change in slope in chemical potential, I see a jump in enthalpy, which means I have an infinite jump, an infinite heat capacity, as I have a non-continuous second derivative of chemical potential. And this is exactly what we end up seeing with heat capacity, is that once we reach the phase transition, our heat capacity technically goes till infinite, but um, in practice, it essentially just sees a large or spontaneous spike, and then we go back to another linear correction. So most of our phase transitions that we're familiar with are going to form these first order Ehrenfest transitions. And this is largely due to some sort of change in the chemical structure involving a change in bonds, thus leading to our discontinuous jumps in volume and enthalpy. However, it is worth noting that there are a certain subset of systems in which not only do they have a continuous change in chemical potential upon heating, but they also see continuous changes in volumes, enthalpies, and entropies. However, they're also still going to see a discontinuous change in heat capacity. But one of the things to watch out for is, even though we're going to see all of these values be continuous, their first derivatives are still discontinuous, as demonstrated by the heat capacity. So again, one way to think about these systems is I'm going to see some sort of slow change in the chemical potential. I undergo a phase transition, and then I move into a new kind of chemical potential regime. Another way of looking at it is what's happening on a volume level. So let's say as I heat the system, I see some sort of expansion or compression. But let's say as I heat my system, it starts expanding, and then temporarily the lattice of the structure matches up exactly with the same chemical structure of a different phase. So it slowly starts expanding in a different direction. This is often very common in certain electrochemical materials, as you'll end up heating them and they'll expand to, say, along the x-axis, and then at a certain point it now becomes more favorable to expand in a different direction, say the yz plane. And so we'll see a change in volume with now a different, essentially, slope. And you're going to see something very similar with the enthalpy, that you'll see this continuous matchup, because at this one point, they're going to, for a very temporary moment, both structures are going to share the same lattice, and then they're going to see some sort of change. And because we see this behavior with enthalpy, we see it for entropy. But you're going to notice, because these two systems see a different change in enthalpy, even if the enthalpy or IMFs temporarily match up, but because the change in enthalpy is different, we do see this discontinuous feature in the heat capacity. So again, one of the ways to think about it is we see a smooth transition in the chemical potential, discontinuous first derivatives of the dependent functions, or alternatively, a smooth first derivative on the chemical potential, and a discontinuous set of second derivatives. And this is a good way to try and look at how phase transitions happen. So again, while first order phase transitions are the most common, it is important to realize that second order phase transitions are out there. And one of the more popular examples is alpha beta tin. So these two structures are substantially different, but when they undergo a phase transition at -40 degrees C, tin can essentially move from one lattice structure to the other lattice structure essentially continuously. This is most commonly known as tin rot. And so what you end up seeing is you have your nice nice set of shiny uh, uh, shiny beta tin. So beta tin is what we often think about when we're thinking about tin. Alpha tin turns out to actually be non-metallic in nature. It's essentially dull in color and very brittle in structure. And it turns out that they have a phase transition that happens at about negative 40 degrees C. So this is again where the phase transition is spontaneous and all those transitions are going to be continuous. However, if you then say heat the material up again, you're now say stuck in the alpha tin structure and you're a little bit in trouble. And this actually uh, the most famous apocryphal stories of alpha beta tin transitions actually date to the Napoleonic Wars, where Napoleon's armies marched into Russia with nice, bright, shiny tin buttons, holding their uniforms together. And when they marched back in the middle of Russian winter, all of their buttons had degraded due to this tin rot. So again, in practice, most of the important second order Ehrenfest transitions often are going to show up um, um, in electrical materials, and they're often much more rare in nature because, again, they require this very special feature where, at least for the one point of the transition temperature, all of the physical properties essentially match up and you can move from one substance to another. So hopefully this makes sense, and this wraps up our description of pure phases. Next time, we're going to dive in to that complicated topic of mixtures. Till then, take care.